8a, and 8a says you're going to define and use the concept of a mole. And if you need to pause the video, set things up, do that now. A mole, and I'm going to give you two definitions for a mole. The first is going to be like the textbook definition, and so you can kind of get an idea of where they started talking about this stuff. A mole is the amount of substance that has particles equal to the number of atoms in 12 grams of carbon-12. It's the amount of substance that has particles equal to the amount of atoms in 12 grams of carbon-12. Okay, so there are two big substances in chemistry that we compare everything to. One is water. Everything's compared to water. The other is carbon. So there's a precedent set for that. This is a nice kind of way of saying that, you know, they started out talking about 12 grams of carbon-12, and remember that when you have the symbol and a number beside it, they're talking about a particular isotope of carbon. So all of them have 6 protons and 6 neutrons. The more practical definition for a mole, however, is the amount of substance that has Avogadro's number of particles. When I say amount of, I'm talking about grams. So the amount of substance that has Avogadro's number of particles. And Avogadro's number is a very specific number. Just like a dozen is 12, Avogadro's number is 6.02 times 10 to the 23rd. It's a big, ugly number, but you have to have such a big, ugly number because atoms are so incredibly tiny, tiny, tiny. So it's the amount of particles that has Avogadro's number of particles. So it's the amount of the substance that has Avogadro's number of particles. So again, if you have a ream of paper, it's 500 sheets of paper. If you have a dozen of something, it's 12. If you have Avogadro's number of something, it's 6.02 times 10 to the 23rd. Now, we need to make that more realistic. And so what we can do with this number makes us be able to use the numbers that are on the periodic table actually in the lab. Because if we look at the molar mass on the if we look at the mass number on the periodic table, it's just protons plus neutrons, right? Totally worthless number to us if we want to use it in the lab. But what we can do then is we can say, well, let's not talk about it being the mass number, let's talk about it being the molar mass. It's the mass of 1 mole of a substance. So if I have 6.02 times 10 to the 23rd particles, then it's going to be 1 mole of something. So in this case, it's the mass in terms of grams. And specifically, it's the mass of 1 mole of any substance. So take out your periodic table. If you have 1 mole of carbon, then that 1 mole, that 6.02 times 10 to the 23rd particles, is going to weigh 12.011 grams. And that's going to be 6.02 times 10 to the 23rd. If you have 1 mole of oxygen, then that's going to weigh 15.999 grams. And that's also 6.02 times 10 to the 23rd. Just like you can have a dozen marshmallows, they're not going to weigh the same as a dozen eggs, right? So just because you have the same number of pieces of it doesn't mean they're all going to weigh the same at all. For example, again, if you have 1 mole, and a mole is abbreviated as MOL, you just kind of drop the E, so there's not much of abbreviation, but I'll take what I can get here. If you have 1 mole of nitrogen, well, let's do 1 mole of sodium. Let's get a metal in there. If you have 1 mole of sodium, it's going to weigh 22.990 grams. So what we've done by making this relationship between number of particles and moles in the molar mass is that we've created the setup so these numbers on the periodic table are going to be useful now. We can go back and measure out 12.01 grams. We can go back and measure out 26.982 grams. And we know that that's a numerical relationship because they all have 6.02 times 10 to the 23rd particles in them. Now, we can also do the same thing with a compound. So we can talk about the molar mass of a compound, which is really useful because most of the chemicals that we use are not pure elements. They're going to be compounds of something. And this is the mass in grams of 1 mole of a compound. So if I'm talking about water, water's H2O, I have 2 H's, and if I look at the periodic table, each H, hydrogen, weighs 1.008 grams. So if I have 2 moles of it, each one's going to weigh 1.008 grams. I have 1 oxygen, and I look on my periodic table, and the oxygen is 15.99 grams per mole. So I do the math, and I have 2 times 1.08 is 2.016. 1 times that is 15.999. And I add those two up and I get 18.015 grams. So if I want 1 mole of water, I have to go back and mass out 18.015 grams of water, and that's what I get there. We can do this for any compound that we have, and we're going to practice on that in your packet. We also call this molar mass. You're going to find a couple of other names. They call it formula mass or molecular mass. If they call it formula mass, they're talking about an ionic compound. If they call it molecular mass, they're talking about a covalent compound. It's kind of like saying, if we use molar mass, it's kind of like saying, let's talk about humans. And if we use formula mass or molecular mass, we're kind of like saying, here's males and females. So a lot of times it's easiest just to use molar mass because it's more generic and we can talk about it that way.